Hello, my name is Julian Drebeck. I'm the CEO of Neptune Robotics. Neptune is a robotic underwater technology company from New Haven, Connecticut. We're excited to be here at the 2017 MATE competition to debut our most recent vehicle, Isaac. Isaac compiles our many years of experience and is the most advanced vehicle we've ever produced. It's designed for work in busy ports such as that of Long Beach, California. It can work on the construction and maintenance of mechanical systems. It can do search and recovery and various scientific tasks. Some of the special features that allow it to do this year is a compact size that lets it get into smaller spaces and be more maneuverable, a rotating manipulator which has the strengths of many tools in one, and vectored thrusters which will give us more control over where the vehicle goes. Before we go into the technical aspects of the vehicle, we have to talk about safety, as it was very important to our team. So I'm going to pass the mic on to our safety officer, Mac. I think we said don't say pass the mic.
I'm Mac Bethke, I'm the safety officer, and safety was the most important thing when it came to building the ROV. We had to worry about safety while building the vehicle, such as with power tools, in addition to having to worry about safety at the competition and during transportation for things such as making sure motors are properly labeled so no one gets cut, and proper techniques for lifting the vehicle. With Frame, we have Alex.
Hello, my name is Alex Hodge, and I led design and design rationale. So, the first thing that we figured out for our ROV was size. We wanted to make it very small and compact to minimize the amount of PVC we used, and to make it the most maneuverable as we can underwater. So by doing so, other things that we added to the frame were crossbars here, here, and we added a mount for the manipulator here. Doing so let us mount the cameras in the optimal positions to watch motors, watch our manipulators, and so that we can see. And we also put skis to leave room for the manipulator. A lot of problems that we came into while designing that we had to overcome was we overcompensated and made it too small, so that we couldn't fit these things like the motors, the cameras, and the manipulator with not it all clanking together. So to do this, we widened it and made it a lot taller and added the skis. We also drilled holes into the skis for variable buoyancy, which is another part of my frame rationale. And with that, I'm going to pass it to Josh with propulsion.
Hi, I'm Josh Graf, and on this Neptune Robotics company, I was in charge of propulsion, which means motors. Now, our ROV, Isaac, has 6 motors. It has 4 motors that provide lateral movement, allowing it to both pivot, slide, and move forward. It also has 2 thrusters that give vertical movement, giving it 4 degrees of freedom total. The motors we chose are attached on the corner bars of the ROV with click clamps. The motors are bilge pump motors. We reused them from a previous year, but on today's market cost, they would each cost around $35. Motors are controlled with wires that are conducting through the tether, and Brian is going to talk about that.
Hello, I'm Brian Brigham, and I was part of control. So, with control, there's 3 main parts. First, the dial board, the switches, and the relay block. So, as you can see with our control box here, from the switch, power goes from the switches, then goes to the diode board, which in the diode board distributes the power to 4 of the 8 relays, which then give us the movements with our thrusters. With that, with the different types of, with the diode board and the relay block, we were able to make it do everything Josh said with the pivoting and all that. So, and one of the main problems we had was the diode board. We bought a prep board, which didn't quite work out for what our use was. So we had to produce our own, which then made it much more made it much more affordable, and made it work better for the ROV. Now that I've gone over the control, I'll hand it off to Marissa, who will be talking about tether.
My name is Marissa Rodriguez, and I was in charge of tether. Our current tether consists of 10 wires for thrusters, 2 for video and camera cables, and 6 for payload. We had to take apart the tether a few times because our video cables weren't working, so we replaced the 3 original cables with 2, and we also pulled out pneumatic tubing, and more to talk about that.
So as Marissa said, we pulled out pneumatic tubing because we decided an electrically controlled manipulator would be better. It's more reliable and also more powerful. Now in the past, the company has had vehicles with a vertical manipulator, a horizontal manipulator, and a separate rotating tool. But this year, because size was such a big consideration, we wanted to combine all of those into our one rotating manipulator. It has 3 prongs and it rotates, which allows it to grab objects at any angle, and it can also turn valves. It was designed on SolidWorks, prototype there, then 3D printed out of PLA at a local makerspace, and further prototyping was conducted. In order to rotate it, a motor mounts here, and a gear spins these teeth. Some of the problems we ran into it, on SolidWorks, things can have the same diameter, but on the manipulator, in real life, we had to make things smaller. And also, these supports weren't supported enough, so I had to add ribs that gave them better strength. With this tool, our ROV is capable of a lot of tasks, but for some others, we had to make a different tool. That's the winch, and Brendan's going to talk about that.
I am Brendan Myers, and my payload tool of specialty was the winch. As you can see here, the winch is comprised of a bar, a car door gearbox, and a spool of cordage. Now the cordage is marked off every 10 centimeters by a piece of black electrical tape, and every 5 centimeters by a piece of yellow electrical tape. What this winch allows us to do is measure the distance between 2 different spots, with us knowing the distance within plus or minus 2 centimeters for every 1 meter, which is a pretty good margin of error. Now, originally it didn't always begin this way. At first, when we first heard about the specs, we wanted to do a kind of drawbridge kind of thing, where the winch would lift up the drawbridge and capture any things we had, such as samples. But very early on, we realized that this was not the greatest idea because we needed to do things such as turn valves. But as you can see, our current design is the best design. And with that, I shall be passing it off to Damien with camera.
Hello, I'm Damien Kopek, and I was in charge of cameras. And cameras were very important for almost everything in our payload. We needed to make sure that we had a camera so that we knew where we were going. We also needed to make sure we had a camera so that we could see the winch. So when we're measuring things, we could look how many marks were on the, so we can, like how many marks, 5 centimeters, 10 centimeters. So we actually knew how far we were pulling it. The cameras are attached to the frame with click clamps, and they have power and video cables that go into the tether. And these cameras will be able to see everything on a TV, and we will have 2 cameras, and we'll be able to switch channels so that we can look at the different cameras that are on the ROV. And with that, I will be passing it off to Max for buoyancy.
Buoyancy was one of the most important things in the vehicle because if it wasn't neutrally buoyant, we wouldn't be able to control it as precisely as we would have liked to. So we have a neutrally buoyant vehicle that is controlled using air ballasts, which you can see on the top of the vehicle, and that allows us to change whether we want positive or negative buoyancy based on what the customer requests. And now John with testing.
Hello, John Gonzalez, and I conducted a test called a bollard pull test, where the motor was connected to a string, and the string connected to a spring scale, The purpose of the test was to test the different types of brass propellers. We had two different ones, and the one that we used on the ROV rates of 6 newtons. From there, after we put the motors on the ROV itself, we connected to the control, and we decided to take it for a test. Right. The first test, there was a misconnection with soldering, and the signals was very slight, and it wasn't getting as powerful as we wanted it to be. We took it back and replaced it with another wire, and the second time that wire was too small, so that wire melted. Now when we realized that, we switched it around. The third test, it did perfectly fine. The motors were getting enough power as they wanted to be, which was 6 newtons. But the issue that brought on the third test was the buoyancy. Originally, we didn't have two tanks up there. We only had one, and we realized that there, and I'm glad we realized it then. From there, you've been hearing throughout this entire presentation that it being small and the money cost was inexpensive. So from there, I'm going to pass it on to Josh with the financing.
Hi, I'm Josh again, financial officer of our ROV team. The team was privately funded with self-run fundraisers, and it received several donations from companies. Now, cost is one of the most important parts of our ROV because it is, simply put, our greatest advantage. As I mentioned before, the bilge pump motors are affordable. They are cost efficient, placing $35 each. That runs the total propulsion system at just over $200. The PVC is very cheap, and all of the PVC, as well as connectors and click clamps used to build the vehicle at market cost today, run under $50. The manipulator, as Julian talked about, is 3D printed out of PLA, which runs for $20 a roll. We used about half of one roll. The tether itself was a donation by TechFlex. Thank you, TechFlex. And the rest of the ROV was, taken from a car door or reused. With that, I'm gonna let Julian make the closing statement.
We hope you enjoyed learning about the technical aspects of our vehicle. We're very excited to test it in the pool and see what it can do. But before we do that, do you have any questions?